Cool.
Uh,
All right. Thanks, Rob.
no worries. So first up, can somebody confirm you can see a PowerPoint slide? No, I'm not sure you can. It looks like it's
Yeah,
going.
all good.
Yeah.
Yeah, that's a. So you got this. You got a Earth Analytics. You don't have a picture of a map or my head. All right. Zoom is telling me that it's sharing the left-hand screen when I've got a right-hand screen, so it's just a bit confusing. All right, so a little bit of an overview of the Earth Analytics Science and Innovation Hub and its relationship to the Open Data Cube, open source community, and open source library, and also just some of the parts of it that are actually unique and where we're up to. We'll also do a live demo because I feel like living dangerously. So originally, the concept around EASI Hub is actually based on a CSIRO business engagement analysis that was done by myself, Alex, and a few others a number of years ago. And it was looking at our work in Earth observation, data analytics, and general Earth analytics. Actually, I have a minerals background for minerals exploration, as well as the work I now do in Earth observation, which is relatively recent. And what we found is a lot of our technology wasn't really having the kind of impact in industry that we would have liked. And so we interviewed, it was close to 100 organizations by the time we finished, about innovation cycles, working with CSIRO, things like that, and why it is that they loved the tech that we were producing but weren't really picking it up. And what we found was a set of key messages, and that's what EASI Hub has been built to do. It's designed to accelerate the technology transfer from our research and development outcomes through to use, and really starting to move away from a situation where research code is produced to produce a research paper. And what we actually need is digital services that can be used and incorporated by industry into their architectures. And by industry, I mean industry, government, other academic organizations, and that type of that kind of engagement where they can actually make use of the outcomes within their workflows, not just within ours. And that means you need to be working on a production ready infrastructure, one that can actually scale, that self-repairs, and provides that kind of robustness that you require from a platform that you depend upon. So EASI is around that activity, and that's why we started building EASI in the first place. The Open Data Cube as a community, and we are a member of that community, is really around doing the analysis of Earth observation data. It's a Python library and a community developing that Python library and an ethos around analysis ready data. And that's about having that Earth observation data available and having tools necessary to perform that analysis. So EASI is a combination of a business strategy and a makes use of the Open Data Cube libraries and supports that community amongst other libraries and communities that we are involved with to make EASI Hub work. So the type of work we do varies in CSIRO, like it does with the Joint Research Centre. This is actually a total cover analysis for the whole of the continents done by a colleague of ours, Juan Pablo Gershman. And so we do have data that and processing that does get to the continental scale, and we work from everything from paddock scale through to global. There's actually a version of this that runs globally. And we have everything from urban planning through water quality people like Tim, through marine stuff, through forestry, through agriculture, and so forth. So it's quite an ask to build a system that's capable of handling this. I should also mention this. We have, along with all the Earth observation capability, we also have staff like myself who are computer scientists and software engineers, and we build tools like the one you can see here. This is the Terrier Cube portal, and it's running in a web browser. You can't see the web browser around the outside, but it's just this is all in the web portal. And that's actually written by some of my colleagues in CSIRO's Data 61 business unit. And it connects through to a web mapping service, a standard OGC web mapping service that is part of the Open Data Cube tool suite. And it's capable of producing this type of visualization. I'll show you a live one in a little minute. The Open Data Cube itself, for those that aren't familiar with it, its underlying claim to fame is it helps to provide you with access and organize analysis-ready data that is actually aligned over time and space, so that you can perform relatively straightforwardly deep time series analysis at scale on the data set. So all of the munging that's required to do atmospheric correction and geometric correction for the data is done um, prior to you accessing it in the Open Data Cube. And then you can perform analysis on that using a variety of Python libraries that go beyond where the Open Data Cube itself finishes. In the CSIRO Earth Analytics Innovation Hub, we have a number of analytics libraries. We have the ODC, the Open Data Cube. We also make use of another community's suite of tools. Pangeo, like ODC, is a community, and they support a range of open source libraries, primarily for things like climate science. All right, so they're coming at ODC. You can think of ODC's focus is around making Earth observation data analysis easier. Pangeo's focus is around making climate type data science easier to do. They both have an interest at a mathematical level on processing arrays of numbers. So as a result, you would expect, and there is a considerable amount of similarity in the core libraries, to the point at which in CSIRO's world, where we do both climate science and Earth observation, we can combine the data sets relatively straightforwardly in the ecosystem. More recently, we've started adding in some of the machine learning libraries like TensorFlow, and I expect in the first quarter of next year, we'll be adding full GPU acceleration to the cluster. But that'll scale up as well. So we'll be having full deep learning, machine learning workflows shortly. But you can actually access anything in the entire Python data science ecosystem, and that provides you with a lot of capability. In addition to this, we've got our international relationships through the Committee on Earth Observation Satellites, which have helped to improve data access. I'm currently the chair of the Working Group on Information Systems and Services within CEOS, and it's our working group helps to coordinate interoperable data access across all of the space agencies that are members of CEOS, which is almost all of them. And so our goal is to make that Earth observation data available, and we have a major initiative underway at the moment around analysis-ready data and the publication and best practices of that data onto large cloud providers like Amazon. So many of you would have seen USGS Collection 2 was released globally on Amazon in the US West region. And we work across with them and European Space Agency, JAXA, etc., to help develop best practices in that field, or at least try and keep the whole situation manageable so we don't diverge so much that it becomes very hard again. So we try and influence the ecosystem as well as do our tooling. As I mentioned, EASI is all about these partnerships and getting things to market and in use. And addressing these. Internally, we use it for addressing our industry and government scientific challenges. We use it for training, capacity building, running. In fact, there's a workshop on next week. We have an EASI hub deployed in Latin America, in Chile. It's part of the Chilean Data Observatory project down there. They have a workshop starting on Monday, a hackathon. They were expecting 15 teams and about 50 people. They've got 49 teams and 116 people turning up, and it's all running on an EASI hub deployment in managed by them in US West. So that'll be an interesting exercise for them this coming week, but shows the growing interest in Earth observation data. In terms of its capabilities, I've already mentioned EASI makes heavy use of analysis-ready data. That's not just data coming from satellites. As I mentioned before, we can handle the climate type data. We can also do geospatial data, in situ, data streams, and so forth. Because it's part of a Python ecosystem, you have that full power available to you, and can start to combine it in interesting ways. The data and the compute are together, so it's ready to run. Individual users get to have their own cluster, and I'll demonstrate that momentarily. For the Earth observation data, you're dealing primarily with pixels, not files, courtesy of the Open Data Cube. So you select your region of interest, Data Cube figures out how to make a data cube out of that out of the million files that you just accessed. The potential exists to extend beyond Earth observation arrays, and we've already started looking at some three-dimensional additions to the data cube, and also for higher spectral measurement bandwidth through hyperspectral sensors, as well as also additional LiDAR support and so forth. And we've got examples of that within CSIRO's EASI hub that have processing pipelines that will enable that to be used with alongside the other data types, including Earth observation. The exploratory data analytics environment is the one that I certainly prefer. We use Jupyter Notebooks and the Jupyter Labs interface for performing a lot of our work. We also support the ability to do publish dashboards. So you can publish your notebook as a dashboard without the code being visible, but with a fully interactive user interface still. And of course, we can do things like deploy web applications like the Terrier Cube you saw before. And there are others you could do within the environment. Users get their own custom cluster that they can specify parameters for, and the entire system auto scales on users and compute, and potentially to extraordinary levels if your credit card is large enough to pay for the cloud time. We also have a fully automated workflow for handling data conversions and additions to the system. If this is actually a bit of a block diagram for some of the workflows associated with the standard Earth observation data coming from ESPA, USGS, and the ESA Copernicus Open Access Hub. You'll note there's a couple of paths here. One is actually you can order data, and it'll be processed through the ordering system and then indexed into the EASI hub. And we'll actually make a copy of that data and store it in our hosted data on S3. The other path it can go is it can come in directly from the cloud, and these two links now exist. Both USGS and the some of the ESPA, some of the ESA archives are now available directly on AWS. In which case, we don't actually store the data; we just use it in place. Some of that data, like the Sentinel-1 data, has additional processing steps required for use. And we can plug that in as well as bring in the GIS data sources. And we have a pipeline for doing this that's automated. It'll trigger when new scenes come in over the area of interest and publish that up. I'll skip this bit. This is an example where the Chilean data cube was loading up Chile. It's an automated system. You can see it's just run over time. There's a few red boxes. That's where ESPA was actually down. It actually went completely down for a few days down here. And the ordering workflow just says, okay, it's down. I'll wait another 12 hours and then I'll download it, try again. And it carries on until it finishes doing the download. So getting all of this data took about a week, although I think 3 days of that was actually ESPA being down. So that was pretty cool from scratch. And I think at this point, I will grab this window and show you a pretty picture of it actually in use. So this is Terrier Cube. As a portal, it's a standard web mapping portal. We're actually looking at a region in Vietnam. We've got data just sitting over Vietnam because we're doing some projects in Vietnam at the moment in CSIRO. So when you zoom out too far, it doesn't bother showing you the data. But when you start zooming in, it'll actually do the processing on the fly. So we're showing here just a simple RGB without clouds. The cluster in the background, because I'm now hitting it, will be scaling up the number of workers that are available. Now you can see the cloud masking is working perfectly over here, not. But you can see here, we've got just some Landsat 8 over the region of interest, and it's just pulling the clouds out. Now this product's being generated on the fly. This product is not stored as a cloud-free product. It's stored as raw Landsat data, and it's actually doing that masking on the fly. You can see it a little bit more clearly. This NDVI calculation, which is doing a per pixel NDVI over the region, is also being done on the fly. We don't need to store for this type of simple processing. We don't need to store an additional product. We can just do it on demand, and the performance is okay. for the most applications. You may actually notice that it's hard to tell with video if it's coming across to you, but it's actually got faster. And the reason it's getting faster is because I'm hitting the cluster and the cluster's started more workers and scaling up under load. And that would happen if there were more users hitting the system. It would continue to just grow up to some limit, which is usually not the size of the Amazon cluster. It's usually the limits to your spending capacity. So this type of thing can happen. You can also do enhancements to this interface to add additional time series lookup and pixel drills and mosaicing and all sorts of things. But they're all standard tools, but just showing really that this exists. And the web mapping service that's underneath here that's supplying this page will work with something like QGIS or ArcGIS Desktop. So you can just connect the data to the web, those GIS packages to the web services, and they'll display. In terms of the actual analysis, this is, I should just clear out the outputs from the previous run so you can see what's going on. This is a Jupyter Labs exploratory data analysis environment. We encourage our data scientists to use these types of environments for exploring their data. And over here, I'll just shut this down. There we go. When you first start up, you start with just your user node. You can do processing directly on here, but if you want to, a user can simply ask for a cluster. So they can come over here, hit the new button. By default, they'll get a cluster with 2 workers, and you can see my cluster has started up. I've now got 16 cores and 60 gigabytes. I can actually tell it to be an adaptive cluster and let it scale to say 5 workers if it needs them. And that can be important for performance, depending on your application. It isn't always the case that bigger is better, but in this particular scenario, 2 to 5 will do us just nicely. So I can connect to my cluster from my notebook, and then I've got a little script here that's just going to do an NDVI time series analysis. So I've got the Tumbarumba, I think that's how you pronounce it. I've never been there, but it's somewhere in Queensland, I believe. I've got a buffer. This is a radial size, so this is actually a 0.125 by 0.125 degree region we're going to do an analysis over. I've got 2 years worth of data, and I'm going to load up Sentinel-2A, Sentinel-2B, Landsat 5, 7, 8, reproject them onto the same grid and sample size, which will be at 30 meters because that's the maximum resolution of the Landsat 5, 7, and 8. And we're going to do an NDVI calculation on that data over that time period. So you can see we've got a relatively small chunk of data going to be coming out. It's 500 pixels by 400 pixels, 320 time slices over the 2-year time period. And I can bring up a little map. I can zoom out a little bit. You can see the red box of where we are. If I zoom out far enough, for those of you not familiar with Queensland, we are, well, we're not in Queensland. We're in New South Wales. There we go. I've got it wrong. We're in New South Wales. That'll do. Zoom in a little bit. You can tell I don't know my geography. And I can draw myself a little region, and it'll compute the average NDVI for that little patch. And we'll turn on the little taskbars so you can see what's happening. Cluster quite happily goes off. And it'll process that data for us. Now you can see it's using, it's grown to 5 workers to do this. So there's 40 cores processing. So you can see the 40 threads here doing the load. And over here, you can see the progress bar for the various tasks that it's split it up into. And here we can actually see the NDVI results. Now you'll have to excuse me. These little anomalies here are most likely my not masking something correctly and cleaning up the data. But the general trend is it was green and then it burnt down and it was not green because this is January 2020 just here. And you can see it's actually the impact of the fire can be actually seen in the NDVI over this region here. And it's actually greening again by the look of that that looks like a trend to me, but I'm not an Earth observation scientist, so I'll leave you guys to decide that. But it looks like it's growing back from my perspective. I could actually choose another region if I wanted to. My red box is the area I've got loaded, and I can play comparison over that additional region. In fact, I could draw several. And it'll perform that calculation. Again, if I wanted to, I could let the cluster scale up a bit more. If there aren't available compute nodes to run at the moment, it'll start them on my behalf. It's probably doing that in the background now because they didn't come up instantly. So you get the idea. I'll let that finish in here, and I'll just introduce you to this other notebook over here. Let me put this one over here. So in this notebook, I've got a slightly different approach to the visualization going on. Again, we can actually reuse the same cluster. If I wanted to, I could actually start another cluster. Yeah. And then I'd have just have lots of them. But I can actually reuse the same cluster and just have the two notebooks taking turns. I'm actually going to shut that one down because I don't really need to. And I can connect to it, and then I can go through, and this is going to load up some just Sentinel-2 data. It's going to be the same region, but it's a much larger area. I'm grabbing a 1/2 degree by a 1/2 degree. And we're going to look at a 1-year time period between the 1st of June and of 2019 and the 1st of June 2020 over that area. Again, you can see here now we're showing more of the code. In here I had the code, a lot of the code was hidden. It's finished that calculation. You can now see we've got 3 different colored polygons and 3 different colored time series, and they all burnt down in that time period. So over here, we'll load up a larger amount of data, a much larger region. Sentinel-2A, 2B, 1-year period from June to June, and tell the cluster to load the data. It can tell us, we can do the cloud masking. A lot of the commands in the data cube, you're only required to provide, if you don't have any loops here for looping through the arrays at all. You just tell it to process the arrays and it figures out how to parallelize it on your behalf. That works a lot of the time, not all of the time. This is a 34 gigabyte data set when I run it this time around. And I'll just stop here for a moment. You can see here the math using a library called X-array is pretty straightforward. DataCube loads in all the Earth observation as an X-array, and you can simply specify the bands you want to do math on. So near infrared minus red, near infrared plus red, divide the two, that gives you an NDVI. And that's all you have to do. That whole calculation will be parallelized and do every pixel on your behalf. I'll skip some code here. And if you want to do a monthly average, you can resample time at a monthly basis, do an average for it. And I'm persisting the result out onto the cluster because I'd like to actually visualize the result. So for some reason, those windows like to die on me. We've got the full dashboard over here, but let's have a, where are we? Progress bar, there we are. You can see it's alive. Bring up the task stream. We're just using 5 workers for the calculation at the moment. I'm actually going to give it a higher upper limit for reasons that will become apparent in a moment. You can start those while this calculation finishes. Now, the thing to note, this data set is larger than I'd really want to visualize in my web browser. So what we're going to do is we're going to actually use the cluster to do the visualization. So we're using a library here called HoloViews, It's going to draw us an interactive visualization, but all of the rendering will be done on the cluster. It'll resample the data and provide me the average pixel for the region of interest. And then we can actually interact with that data set without too much difficulty. And that allows you to visualize data sets that are really quite massive. I was playing with one that was nearly half a terabyte the other day. So let me kill these other windows so you've got a bit more room. We can see here we've got the area of interest. I can actually look through this over time and space. So I zoom in a little bit. And you can see the cluster is actually working out what resolution I need to be at as I go. I can zoom further in and you can see it just re-renders each time to give you the imagery in the area of interest at full res. And I can actually go over through September, October, November. I might just zoom out. And you can see here in December, things changed. And by the time we got to January, things had changed fairly dramatically in this region. And that'll be the bushfires going through. So that, again, you can see the visualization and interactive capabilities here. What I'm going to do just briefly, just to give you a bit of an idea, this calculation may take a little while. So we'll just let it run in the background and we can have a chat. But if I change this to a much larger area, so we're now at 10,000 pixels by 12,000 pixels. The data set's 558 gigabytes. You can probably hear Alex's credit card crying if he came off mute. And we can do the same calculation. But now over a much larger area. Where's my, oh, there we go. The graph wasn't starting up. Here we are. Wonderful. And you can see the clusters actually growing as we do this. We're getting more threads on the top. Processing time just continues to grow as it needs to. And it'll chew through that data set for us and spit out the result for us to visualize in due course. So just while it's doing that, I'll park that over here. And so you can just see it moving along in the background. In terms of the data holdings, we can actually view our data holdings online with this Explorer interface. This is some USGS ESPA supplied Collection 1 aquatic reflectance data. We've got this in regions that are of interest to the projects that CSIRO is doing. So we've got some over Lake Hume down here, PNG, Timor, Sarawak's in there somewhere, and Vietnam for a relatively modest recent time period. But we also have things like the Digital Earth Australia Landsat archive, which I can't find. There it is. For Landsat 5, 7, and 8 are all on here, and they're full archives for continental Australia. Something like USGS, ESPA, Landsat 8, surface reflectance, we have that in a number of regions. California's got some over here, which is why this is so zoomed up, and over pockets in the Southeast Asian regions while we're working. You'll notice we don't have, there are gaps here. That's deliberate. The projects aren't requiring data in certain time periods yet, so we haven't got those loaded up. We load up data as we need it for our projects using our data pipelines. We also have a lot of the derived data sets that are produced by these groups. There's fractional carbon products produced. There's water observations from space data, and all of this is available online And you can see the coverage. You can actually zoom in to these and look at the individual data sets and see where they are if you wanted to. And also the metadata shows up. I should probably do that on the metadata's over here, but it makes more sense if you look at it on something like you can see all the bands on the Sentinel-2 down here, and they've got multiple names. There's aliases for the names in some cases, because some people refer to, like, I'm coastal aerial. Some people like to say band 1. So some of that changes a little bit depending on what you want to do. So there's quite a suite of tools available for interrogating and seeing what's in the system. And my calculation's almost done. Parallelism in the calculation will drop off towards the end as it brings all the results together. You'll see more of these red bars. They're red because transferring data is an operation that takes time and doesn't really do much for you. So, but except for, of course, you need it to get the results. So you'll notice our cluster's grown out to the full 15 workers I asked for as well. And as it completes, it will actually shrink back down again. Oops, sorry, I didn't mean to do that. There we go. So the system itself actually runs on a Kubernetes cluster for those of you that are interested in the back-end activities. Oh, I just had a question pop through. Alex is asking, what's the definition of a worker? So a worker in this case is a compute node. It has 8 cores and 32 gigabytes for this particular configuration, but that can be changed. So you can actually have custom workers in your cluster. So we've got some workers that where the processing is such that they require high memory requirements. So we'll have like 32 cores and 256 gigabytes of RAM on a single node. And other requirements are they don't need as much memory, so they'll only get like 8 gigs of RAM, but they might have 16 cores because they're computationally intensive. So you can actually control those parameters. I haven't demonstrated that here, but you can actually, as a user, you have some control over that selection, and we configure the back end to support that. Indeed, when you log into the environment, you're actually given an option as to what tools you would like in the environment. So you may want machine learning tools, you may not want machine learning tools, you might want the Open Data Cube, you might want something else, you might want some custom other Python library that you like to use. All of those type of capabilities can be customized and then made accessible to users to select what they'd like to run. So we've got our data set back with the average monthly mean. This is a 13 gigabyte data set, which is way bigger than I'd want to send to my web browser. And we can ask the cluster, therefore, to do the rendering for us. This will take a little bit longer because the cluster has to do a little bit more work, as you would expect. It also then has to transmit the result back to me. And that'll be happening in the background. Again, I could bring the progress bars up. We can actually see it. You can see it's doing its little calculations. Most of the time is actually spent doing those network transfers back and forth in the system. You'll note also the cluster has actually shrunk back to 2 workers. So that's efficient use of resources. And then we get our result back. This is at full width for us. I can again zoom into a particular part. And it's now rendering at full resolution. If I zoom out a little bit, we'll end up with 1 pixel on my screen being the equivalent of 1 pixel in the actual image. I can look around quite happily, and we're browsing a tens of gigabytes image. The performance of this is the same if this was this many gigabytes or 200 gigabytes. You'd still be able to just pan around it and look at the results. And I think I'll leave it there for live demos and open it up for more questions and see what you'd like to know.
Cool. Thanks, Rob. Impressive on a number of levels. Questions from people. I've got a couple, so I'll just start with one. So is the intent with this, so just thinking forward, so you're doing projects with this within CSIRO, obviously within a range of Southeast Asian countries and South America. I mean, is the intent that you could have someone come in, and actually I'll pick an example with Tim and Alex on our coach. If you had someone come in and say, right, I've got an algorithm, I've got all these field data streams which are coming in, but what I don't have are three things. The satellite imagery that's updated on a regular basis, an online processing environment, and then an ability to deliver an output, let's say like a web mapping service, which could be for water storage features, it would be water quality parameters and summary tables. They don't have that front end. And then the other part is they want to charge people money for it, for that service. So where does EASI fit in that space? Is it one part and you've got to build the other things around it?
So the two parts that you started with, I've got an algorithm and my data streams, and I know how to combine them. Mm-hmm. If they were yours, so to speak, everything after that can actually be supplied via EASI Hub.
Right. Okay.
Right? So you deploy that contribution into the EASI Hub, and that's what we were seeking to achieve. There's a bunch of stuff on all the projects that's basically very, very common, all the undifferentiated heavy lifting, including in our case, because this is designed as a commercial platform, the business modeling and the pricing and the operating cost monitoring and so forth. I mean, some of that we're still baking into the system as we learn what it is that our business model actually needs to be to really engage with our clients. But we've got a couple of commercial clients coming on board now. And that feedback is we're using that to improve how we do simple things like working out what it actually costs us to run the job, and then we can mark up from there in order to charge the customer. We also have the pricing models for different, like we call them t-shirt sizes. Do you want a really big processing data cube or a tiny one? And so you got small, medium, and large, extra large in my case. And so so that's EASI Hub's all about that latter part. It's how do you get somebody like yours or Tim's intellectual property around the science that they do as an Earth observation scientist, that's good quality stuff, into a production environment that can be commercially facing as quickly as possible.
Okay. Right. Thanks. That answers the question. I think Jim's got a question.
Yeah, thanks very much for that, Rob. The question I have is why ODC? So we found it's not performant for time series stuff. Is it the community why you went with ODC, or is it because since you're using the cloud, you sort of get away from a lot of these IO issues which we're trying to handle in New South Wales right now?
Yeah, so performant around spatial or time is really determined by how you chunk up your information, particularly on your storage. We're using so it's no worse in its performance with regards to time and space if you order the data by time or space. Take your pick. It's that, and that's pretty much a fact of any compute system with IO. and unless you've come up with a really clever way of overcoming it, in which case I want to know. So that chunking choice, you could actually store the data both ways if you wish to duplicate it. In our particular case, we're actually using the scenes in their original form. All right, so they're supplied as scenes, they're supplied as cloud optimized GeoTIFFs, which gives us some improvements in performance over an ordinary TIFF. For the applications that we're dealing with, it's certainly proficient enough at performance for continental scale time series analysis. So that, I mean, I don't know if that's been your experience, but that certainly has been our experience. And so we are more comfortable with having the data in its original form rather than re-chunked and reordered. That said, if a scientist said to us, I wanted to continuously do time series analysis for a project, we would encourage them to re-chunk it and put it the other way around. Right. And their project can pay for it. All right. It's because we don't store 2 copies of the data in different orderings for the sake of storing 2 copies of the data in there. And what we found very early on in the work that led to the Open Data Cube was the never-ending disputes around what resolution should we use a discrete global grid, for example, what projections should the data be in, what atmospheric correction algorithm should we do, so forth. And it's the stuff of religious wars, all right? Earth observation scientists will be fighting for decades over what my cloud mask is better than your cloud mask, and the aquatic people are particularly bad. Right? So we decided not to enter into the argument, right? So you would have noticed that we have in our Explorer, we have USGS Landsat, GA Landsat. We even have our own processed Landsat, all right, with yet another algorithm. I'm sorely tempted to write an algorithm that actually compares them all and discovers how little difference there actually is between them. But they're special to somebody, and everybody's special. So yeah, so we don't argue about it. Why Open Data Cube? As much as anything else, because we were involved in the precursor work for Open Data Cube at the time, and there weren't a number of years ago, there weren't many other options around. But for us, it really is, Open Data Cube is very compatible with the rest of the Python ecosystem. We have control over our own destiny, which is important for, particularly for our commercial engagements. We have, can't go into details, but we have, because it's commercial in confidence, but there's a whole range of much lower level improvements that we're making to Open Data Cube around GPU acceleration, machine learning inference engines, and a bunch of other stuff. And a lot of that you wouldn't be able to do if you didn't have like deep control over the source code. And we have that in our environment. So that's the Open Data Cube for a range of reasons. Performance is sufficient. So we don't worry about trying to tune for the world's greatest performance. Could I make it go faster?
Thank you. No, thank you. This helps. That helps a lot. Yeah, we're in the same position with that low level aspect, but versus paying for like Raspberry Enterprise or something for some other things. That's
yeah.
So that helps a lot, man.
Cool. Any other questions? I have a big list of them, but I'm going to let other people ask questions or thoughts, reflections.
Yes, just quickly, do you do irregular grids like the TLS and stuff like that?
I'd have to go into that question in more detail. All right, that we've probably got time for here. Underneath, inside for the non-Open Data Cube portions, things like the climate data sets, absolutely, yes, you can work in that space. For Open Data Cube, there are a number of assumptions that are made within the Open Data Cube code that are biased, they're opinionated around Earth observation data, right? So they're expecting spatial adjacency to hold true. So if you move left in the array, you move left in the ground. All right, it's that type of assumption. And you have some assumptions around, so spatial and temporal adjacency and array adjacency assumptions kick in. That can hold up for some of the irregular grid types, but not for others. And it's a little hard, without going into more detail, it's a bit hard to tell whether or not the Open Data Cube, if you indexed it, would actually behave correctly. Right, but certainly the X-array libraries and all the other Python data stuff in that space does. That's why we use it for the climate data.
Thanks, man.
Thanks, Jim. Any other thoughts or questions? So just while people are thinking, so this is primarily based around AWS. Are you, like, you would be able to pull in data or use other processing environments, or is this going to be tied to AWS long term?
So we are looking to port EASI Hub over to Azure Cloud, and some colleagues of us have ported a much simplified version of the environment to Google Cloud Platform. And that one can actually consume Google Earth Engine data. But technically, you're not allowed. I believe the licensing prevents you from connecting a AWS version of EASI Hub to the Google Earth Engine data, pulling it out of the cloud. Although technically it's possible, I don't think you're allowed to.
No, I think the I'll call it an agnostic approach that you're taking with resolutions as well as algorithms is really important, and it avoids getting into that point of where people go, well, you're using that data set, so I'm not using it. That doesn't fit my area. So I guess a point that a number of organisations are at in Australia is going to be, look, we've invested heavily in these large-scale online data stores and compute facilities. They are not likely to be funded going forward. So what are our options going forward? And that's, so there's Digital Earth Australia, there's potentially this. So I don't know that, this isn't a question, I guess it's a point. The environment's moving into that space of where do we go next? And I know that's something that Jim's having to look at carefully within joint remote sensing. And Peter's part of that and a whole range of other initiatives as well. But I don't know where that's going to go in the future.
Neither do we. What I do know in the case of EASI Hub is the reason why we have a business model and a business intent is because we would like it to be sustainable.
Yeah.
And for us, that means accelerating the innovation pipeline, right? Get our science out the door and paid for. So that's what we're seeking to do. We've now got 3 regional nodes for this. There's one here in Australia. There's the one in Chile. There's one in California. And there will shortly be one in Singapore as well. And in those regions, as part of our business model, we actually have relationships we're building with the research universities in that area, and also IT providers. So we can provide both IT support and on-ground fieldwork support for applications that are being developed in those regions. So the business model is actually getting quite sophisticated.
No, I think having that business model helps, and if it's going to be, I guess, transparent and open, I think that's one of the challenges we have with other platforms as well, where they're quite tied to data types and data systems, just Digital Globe and Planet, thinking of those. I've got one more question, but I'll ask if everyone else has got a question. All right, everyone else has another second to think about stuff. Astronomy. So obviously, astronomy is a big part of what CSIRO does. What we're starting to see in a number of areas, and sometimes I'm trying not to be negative about this, some very positive and constructive work where people come from either doing I guess, radio astronomy, interplanetary science, and come into this environment and are like, oh, we already deal with all of your data sets and our stuff is way more complex than yours, blah, blah, blah. Let's build algorithms to solve Earth observation problems. If it's done well, I think it actually works good. But is there much discussion with the, I guess, the data processing groups within the, at least within CSIRO's astronomy area and this type of activity at all?
Yeah, so well, I'll actually jump out of CSIRO Australia for a moment.
Yeah.
The reason why CSIRO Chile has an engagement with the Chilean Data Observatory, that's a radio astronomy group.
Okay.
And they're actually supplying AWS credits because that project, the Data Observatory, has got massive AWS credits. So we actually get to run that cluster for basically nothing, right? Computational cost wise, because of that relationship. And it exists because they saw the potential for some of the radio astronomy stuff. The Centre for Earth Observation, which Alex and I are members of, is part of CAS, the Astronomy and Space Science section. So EASI Hub is actually now housed within CAS. Unfortunately, they're like CSIRO, like most organisations in Australia of this size, doesn't have the conversation that you're referring to between the astronomy scientists and us on the Earth observation side. They just don't. There is probably, given the current, so we've just passing through the hype curve phase within CSIRO. I've literally had in the past 2 months a dozen scientists suddenly start using the clusters, to the point at which that I've actually had to increase the size of the cluster so it could grow to like 100 odd nodes. And I think that's starting to create the conversations and interest that maybe they should be paying more attention. Not that I've actually pushed, to be honest. I've got to focus.
Thanks. Yeah, that was really just to get a sense of where that's going. I may come back to that discussion with the CRC hat on. Because it's one where I think there's a lot of potential. The new Australian Space Data Analysis Facility that will operate out of Pawsey looks like it's going to focus on some of that question of Earth observation, interplanetary radio astronomy, and more in terms of how do you bring people together to have discussions and I guess look at people going across both areas. So, I think I'll make a link there because it's, that's another discussion, right? I'm also just conscious of time and Alex has stepped out as well. So before we close, any other thoughts, comments from people? Peter, anything to add there, or Sylvia?
No, that was excellent. Very good. Yeah, I agree with the agnostic, data provision. I guess that's something that I'm battling with at the moment now that there's, the cogs are available for Sentinel-2 in the US. Do you run with those, or do you run with the JPEG 2000s in EU Central kind of thing?
If you're running on the cloud, you use the cogs.
We've been doing a trial with Kakadu. That's all. So it runs just as fast for most of our applications, but yeah, it's just a bit more expensive with all the GET requests. But yeah, that's the thing.
Okay. So Sylvia, any thoughts or questions?
No, I've got nothing to add. It's very interesting. Thank you very much.
All right, thanks. So just in terms of going forward with this, so the recording, I'll make the link available to everyone, but it won't go outside the Joint Remote Sensing Group, which is the Queensland New South Wales group. There is likely to be a follow-up on this particular area once we start to look at the potential Earth Observation Analytics Hub in Queensland, whatever it ends up being called, as this is something that we could potentially put forward as one of the models that we're using. AWS for very strong proponents of what we put forward, both directly in letter form and indirectly. They have had several meetings with the state government about this. So yeah, so it's all positive. Rob, it's really good to see it get to this point, seeing where things came from several years ago now. So definite advance. But I really appreciate your time this morning, and
No worries.
hopefully we'll be talking again soon on how to take it forward.
All right. Thank you. No, it was great to be able to see you guys again. Particularly given it's like nobody can go anywhere at the moment, or at least you might get stuck there if you do. And,
Maybe that's why Alex came to Brisbane.
yeah, well, he hasn't been on a plane. The guy was starting to get the jitters. It's an addiction, I'm sure. All right.
All right.
Thank you
Okay.
very
Well,
much.
thanks again, Rob. Thanks everybody for your time this morning.
Bye.
See ya.
Thanks all.